Okay, so the first question, right, is on some data sets on cervical cancer data, right? So you can read this. This is a description, all right? This is basically categorical data. Okay, so the data is in the table, right? And so this provides a question on the analysis of categorical data, which you are likely to come across, okay, because categorical data are actually quite common, right? So then I give two sections. One is a main scientific question to help you focus on what sort of question to answer from the data. Okay, so in this case, you have the data, which is a 2x2 contingency table. Okay, and then you have disease status. Okay, whether these people, let me see, let me close this. Okay. All right, so whether they have cervical cancer or not, right? And these people, they were actually diagnosed, okay? And these people is a restricted age group, right? People who are 50 to 59 years old. So they asked them when was their age at their first pregnancy, below or equals to 25 or after 25, right? And then they check, then they kind of count how many of them actually have cervical cancer. Okay, currently have cervical cancer diagnosed, all right? So, and then the question is simple here. So the question asked is whether age at your first pregnancy affect the relative risk of developing cervical cancer at later life, right? So relative risk is you can check up some online sources on the definition of the relative risk, okay? Basically, it's a comparison of the probability of developing cervical cancer in the first group, age at first pregnancy below 25, relative to the probability of developing cervical cancer for the other age group, right? So it's just a ratio of two probabilities. So then you have some kind of estimation of the relative risk, right? Of course, you could also report the odds ratio, right? So you can play around with that. And then that's actually the analysis is quite straightforward. So you may pick a suitable test to see whether there's any association between these two categorical variables, okay? And then the discussion part is the following. Now, suppose you have additional data, right? Like, for example, when the participants were recruited, the investigators also collected information such as number of children, yearly income, occupation, their ethnicity, and number of sexual partners, right, of these participants. How can you use this information to reach better inference about important contributors to the development of cervical cancer? Okay, so maybe you can briefly discuss. Of course, you don't have this information here, but you could actually discuss it. Okay, how you would go about doing some additional analysis if this information were available. Okay. All right, so you can let the marks there roughly guide the amount of work that you need to do. All right, so the amount of marks given there will roughly indicate the depth that you need to go for your analysis. All right, and then you have the second data set on thrombosis study, right? So this is thrombosis is something like a blockage of the arteries by clots, okay? So you have diabetic patients, all right, and normal patients. So then you have it says in order to test for a difference between the two groups, it's advisable to first look at box plots, which expose the skewness. Suitable transformation is required, followed by a test for normality. Now, this advice is very old. In the 80s, this is probably what a statistician would advise you to do. But as we already mentioned, right? So we now already have at our disposal very powerful computational methods. For example, permutation test and bootstrapping. So this advice is actually is already obsolete. You can do it, but I believe it's obsolete because without doing the main reason why this transformation is done is to make the data follow distributional assumptions. Okay, so that the test, when it is applied, there's no issue about the validity of the distribution of the test statistic. But from a consultation point of view, you will end up having a problem, which is the statistical test that you have done is in another scale, right? Maybe in the log scale or square root scale or whatever, depending on the transformation that you have done. So that will confuse your client, right? Your client wants to understand it in the original scale, not some kind of transformation. And basically, the problem with this kind of transformation is that yes, you have done it, you understand it, but your client doesn't understand it, right? Because it's in a transform scale. So there's a feeling that we kind of like make the transformation to satisfy the statistics rather than we try to focus on making the client understand the pattern. Of course, this is no longer an issue now, right? As I mentioned. So, okay. So in this question, you will have to maybe make some comparison between what is the result that you get if you just naively apply your standard test, and then show comparisons with using permutation tests and bootstrapping, right? So later in the second part, I will show you some examples of doing the bootstrapping, right? So you can recycle the R code to complete this question. Okay, and perhaps you can also discuss a little bit about the interpretation. Now you look at this one. From here, there's no indication about the background information of those people who are normal and diabetic. So of course, you know that in order to make a claim that the variation in this urinary thromboglobin is due to the diabetic status and normal status, okay, variation in those two status, the other things have to be more or less equal, right? That means their age have to be more or less equal. The composition of the sexes have to be more or less equal and all that. So this information is not actually present in this data set that you have here. But you may actually try to look at the research paper to see whether such information is reported or whether they actually ignore this, right? And you could include that in the discussion, right? So at the master level, we hope that the students will actually be aware of these issues, right? This is more like an issue about the design, okay? The design of the experiment, okay? So it's not just basically you have a bunch of numbers and just put in some tests and then finish, right? So at the master level, your consideration will be definitely broader, and the design of the experiment will always occupy your mind. It should always occupy your mind, right? So you can refer to the paper for additional details. Okay. All right. So and then you have question 3, diabetic mice. So so basically you have mice, 3 group of mice. One group they are normal, the other group are called something alloxan diabetic. Okay, you can actually go and check what this actually means, right? But technically they just a group. Okay, and then the other is something alloxan plus insulin, right? So they have received some kind of treatment with insulin. Okay, so then they measure the bovine serum albumin, okay, in these 3 groups, all right? So the normal is used as a benchmark, all right? So of course, then you get all sorts of this, there's variation, okay, and the sample size is unequal, doesn't matter, okay, it doesn't need to be exactly equal. And in fact, if you look at the data set itself, right, can somebody give me a suggestion? Why is it that the group normally, right, when you design an experiment, you would actually use the same amount of sample size, okay, for experimental studies. But why is it that the sample size of the mice with alloxan diabetes 2 less, and then the one with alloxan plus insulin is 1 less compared to the normal? Any suggestion? Any explanation from you? It doesn't say here in the question, but it's interesting to think about it, right? Why would the experimenter like use two mice less for the alloxan and one mouse less for the other group? Maybe someone censored. Usually you it's like you keep the mice in some kind of animal room, right? So it's something close. Anybody anybody else want to offer an explanation? Maybe the mice died during the experiment. Yeah, this is probably what I have in mind as well. In fact, this is probably because the explanation that they died is actually quite plausible, because these are mice that are diabetic, and they if the mice has diabetes, right, it's in danger of dying. And this one is treated with insulin, so probably that helps. So so maybe one died anyway, but then you find that you have less death, probably, right? So yes, so this is something that I like to draw your attention to, right? You need to develop some kind of sensitivity to, if you are going to be someone who does data analysis well, you need to develop some kind of sensitivity to data structures, right? So when you look at the data structure, right, just pause a bit before you actually do anything else. Think about the context, and then spend some time to see what might be like for example, like in this case, if you have the chance to talk to the person who have this data, then that was a natural question to ask. Like, so did your mice actually die in the experiment? Okay, so those are the kinds of things that you can actually ask the experimenter, right? By having some preliminary understanding of the data. Okay. So here you can do an analysis of variance. Okay. And again, because this is they were operating on an old concept, so they were worried about skewness of the data. So and therefore whether the F statistic actually is really F. Okay, and the variances are not equally not plausibly equal. So it suggests a simple power transformation. But like I said, it doesn't really, it solves the analysis problem, but it doesn't solve the consulting problem. All right. And you throw a question like this in undergrad, probably this is fine, and do a power transformation and then settle with the p-value thing, right? But at the master level, this is not going to work, right? So the main scientific question will be the percentage of total variation as explained, right? The R square, okay? So in ANOVA, the R square is important, okay? And then you have a p-value thing coming out. So, okay. So you can do that. Those are the main questions. And then a short discussion about whether the result from ANOVA and those that you get from a more accurate test actually whether they matter or not, right? Okay. And then very quickly, we just have about 3 minutes before we pause. So the last data set is on this data set is actually more complicated. Okay, I think I maybe need a bit more time to talk about this, right? So it's close to 7:15. So I think we stop here for now, all right? And then we continue back at 8 o'clock, okay? All right, okay. So I'm going to stop the recording now, and we'll see you later at 8, right? So please come back on time, yeah? Okay, so this data set, the fourth one, is called the byssinosis data set. Byssinosis is a kind of lung cancer that's caused by fibers, right? In this case, cotton fibers. So, so this is actually the more actually a more complicated data set, but at that time maybe, but actually this kind of data set is considered quite standard by today's standard, okay? So, but nonetheless, at that time, this would be considered a challenging data set to do applied statistics on, right? So basically, this is the data set contains this sort of information. So, okay, if you look at this table, right? Now, these are predictor variables, okay? Your so your response variable is either yes or no. So a person actually may have this byssinosis. So these are people who are interviewed. They are all workers in cotton factories, right? So and when data were collected from these people, so they were either checked for this diagnosis, right? Whether they have byssinosis or not, okay? So, and then they record the information about them, the predictor variables, as dust, right? Dust would be the dustiness of the workplace, right? So this is sort of like a kind of ordinal variable, right? High, medium, and low. Okay, 1, 2, 3. And race is either white or non-white. Sex is male for 1, 2 for female. Smoking, whether they are smokers or they are non-smokers, right? And employment length is how long they have been working in the factory itself, right? The cotton factory, okay? So over here, it says, yes, there are 3 people with these characteristics, right? Who actually have bicyanosis. And then 37 of them do not have it, right? So basically, this data set that you see here is actually kind of like, you have to do some kind of processing on the table that you on the data table that you receive. It looks like this, but you have to do some processing so that it becomes a form that is amenable to analysis, right? Because in this form, this is more like a form to store the data rather than for analysis. Because basically it means that you actually have 3 rows of samples where the this vector here 1 1 1 1 1, okay, you have 3 rows with this 1 1 1 1 1 vectors, right? And then with the status yes here, right? So you could use 1 for that and 0 for no, right? And then you have 37 rows where this is all 1 1 1 1, but then the bicyanosis status is 0, okay? So just to show you an example, okay, so it would be something like this. You would have you have to do something like this. Repeat. So that's you have 1 1 1 1 1. You repeat it. Let me see. You let me see. Repeat. Okay, maybe something like this. Let me see. So suppose you have that that's 3 and 1 1 1 1 1, and that's a 37, right? So the first vector would (3 and 37), right? Okay. So this would be something that you have, but you have to convert it to a table, right? Where there are 3 rows with 1 1 1 1 1 followed by a 1. Okay, that's a yes, right? So you have 3 rows where this is 1 1 1 1 1 followed by a 1, and then you would have 37 rows of 1 1 1 1 1 followed by 0. Okay. So so you need to write some kind of processing, some code to process this data, right? And actually, you just need to write one function to process this row so that once you have this function, you can iterate it through the other rows, right? Then you join them together, right? So for example, you would actually, well, let me see how you can actually do this. We can say, call this function expand, right? Over here, you would create a matrix M. Matrix M with start with 0. And how many rows are there? It would be, so this is your data equals to X, right? Okay. This would be the sum of the first two numbers, right? The first two numbers indicate the number of rows you have in the matrix. And then the number of columns will be 1, 2, 3, 4, 5, 6, right? Okay. Right, so that sets the matrix, and then what happens is you could then specify, right? From the rows from 1 to x1, right? The first three, they would be basically 3 until 3, 4, 5, 6, 7, 3 to 7. Okay, and then this is a yes, you put a 1, right? And then the remainder will be from x1 plus 1 to go all the way until the number of rows of m. Okay, and again, this will be x3 to 7, and this you will set as 0. Okay, right? And then finally, you return your m. Okay, so this will be the function. Let's try it. Okay, so then you put expand x. Let's see if it actually works. Well, probably not something that I actually want, because the ones that should be at the 6th column, the ones and zeros should be at the 6th column. Okay, the rest of them should be all ones, right? So how can we improve this thing here? Let me check the code again. That's your x. 1, 2, 3, 4, 5, 6, 7. 3 to 7. One way to do this would be to look at this. All right, so this will be my matrix M. So initially it's all 0. And then let's say if I do this, what happens? Oh, okay. It's x1, all right. This is correct, okay. And then so this should be And over here, I think there's something, it's not quite right. The first 3 rows are fine, okay? But then after that, this is not correct. So the problem must be somewhere around here. Let me see. Could it be n row? N row of m is 40. x1 plus 1 is 4. Okay. And what is this? Okay. Right, so let me change this. M, try this again. Okay. Let me go by the column, right? That may actually work, right? So let me see. M, first column. Let's say for I in 1 to 5. So you can do a for loop here. The ith column is basically your I plus 2, okay? Because this value here will go to the first column, right? And then this will go to the second column and so on and so forth. So that's why there's, because you're starting 2 from X, so there's a shift of 2, okay? And then the last column will be the following. So you repeat X1 3 times. Sorry, you repeat 1 this number of times, X1 number of times, and you repeat 0 this X2 number of times. I think this should work. And M. So let's try that. Okay, so now it works, right? So basically you have generated for the first row of your table, you have generated the required data set, right? So these are all the other, these are basically the people with these vectors, right? There are many people with 11111 here, all right? And the status 111, okay? And so on and so forth, right? So what you need to do is, so later I'm going to provide you with this function, and you're going to, so this function allows you to operate on one row, right? And you just need to make an extension, right? So you're gonna use the function apply. So you're gonna apply on the input table, right? Okay, which you will get in the R data set. The data sets that will be provided. Then you go by the rows, and then you basically just need to expand, and this part here you will be function k, right? And this will be expand k. All right. So basically, if you once you do this, it will generate. You'll basically generate a list, right? I think it will generate a list. So and after that, you can join the list together, right? So let me try to show you. So maybe you have a input table equals to r by xx. So I'm just basically right. Then I maybe change it a bit, fix input table. So maybe I change this to 10. This is 20. And maybe this is a 0, right? Sorry, could be a 2, okay? And again, so, right? And basically, if I do this, what will I get? Let's call this result. Out. Well, in fact, let me see. Expand. Maybe this one is okay. Try that again. So it works for, let me see. Oh, sorry, it has to go by 1, right? Because it goes by the row. So it's not 2, it's 1. So let's try that again. Okay, there's something wrong here. Okay, let me see, input table. So you go by, so we remove X first. Object text not found. Oh, okay, okay, right. So let me see. This one. Object. Okay, I think maybe to make it easy, you could actually just okay, do it like this. I equals 1 in 1 to number of rows of input table. Function X. Oh, it's a typo, is it? Let me see. Because it should work. Function K. And okay. Let's try that. Errors. Check X not found. Oh, okay. Right. I should have done it like this. It should be like this. Then it will work. Because when I put X there, it thinks that it is some kind of you specify some kind of object there. Let's try this again. Okay. It works now, but let's check whether it's correct. Yeah. Okay, it's correct now. Right. So basically, you will get a list object. All right. So this is for the first row. So this is the data that you generated. Okay, the data frame, and this is the second data frame that you generated, right? So it contains 2, 1, 1, 1, 1 with the response variable 1 10 times. Okay, and then the rest of them are 0 times, right? Okay, so that solves the problem. So basically, then this thing you can store it and you call it result, and you need to join it together. So I will show you a very useful function to do that. Once you have a list structure, you use a function called do call, right? Do call rbind results, and you can take a look what happens. Okay, it's the other way around. So result rbind. Okay, let's take a look. Second argument must be a list. Let me check this. List. Oh, okay. Let's turn it into a list. List out. Bind. Let's try that. Not really. Okay, maybe I'll try again. Maybe it's this part. Okay, so this is a list object, so this will work. Let's do call rbind result. List, okay. Result. So you need to join them together. Try it again. I have. Let's see. Oh, because it's already a list. Okay. Okay, this should work already. I don't know, maybe I run it 2 times just now. Okay, so let me just remove this because it's already a list, right? So basically, you just need this, all right? So once you have done that, you just need to run this, and you should get the data matrix that you want, right? Of course, this is just a demo with your input table being just some example, but it's really easy. You just need to read the data, okay? So this is the data file that you will read in, okay? And then that's it, right? Then you store it as maybe you call it BIS-synosis, okay? All right. And then the last step to do this would be to fill in the column names of BIS-synosis. Okay. Let me see. We'll call this BIS-synosis. Let's check that. Okay. The column names are. So you can specify the column names, but actually you can actually read it from the data file, which you will get. So, so the data file, let me see, it will be something like dust, race, sex, smoking, and employment length. Smoking. Okay, and then the last one is your, let's see, status, right? Okay, so you can run that. And this will, object not found. Typing error here. Okay. Right. So then you get the data set like this, right? Okay, and then the last thing is you need to convert this status to a factor because it's a categorical. You have to convert this, you have to specify their nature, right? So for example, let me see. Okay, the dust is actually an ordinal variable, all right? So you could actually, so this, okay. So in fact, you should actually convert all of them to factors, right? So if you check them now, if you look at class byssinosis class, sorry, it's not class, it's operator is invalid for atomic. This column is numeric, all right? You don't actually want that, okay? So let's convert it into a data frame as a data frame. And then each of them you convert the columns into a categorical variable, right? So you coerce it to become a categorical variable by using this as dot factor. Okay. So let's try this. Okay. So basically you will get maybe something like this. I think the code here is a bit annoying, so let me see how I can. Okay, maybe probably not this one. I in 1 to number of columns. Okay, let's try this. Okay, sorry, forgot this. Okay, so let's check it. All right, this is much better. Okay, so then you can actually check the class of a factor, right? So I think all of them have been converted to factors, so that's okay. You can check all of them, right? So so only now that your byssinosis data set is ready for analysis. Okay, for example, you might actually, since your response variable is a categorical variable, yes or no, so then you might want to try a logistic regression, for example. But then this is to show you that if you're going to work as a consultant, right, you need to develop some data processing skills, okay? Because a lot of times the data that's passed to you by your client may not be in a form that you can use directly, okay, for your analysis. And in fact, you can't ask the customer to prepare the data set for you. I mean, like you can't actually ask your client to prepare this kind of data set for you, because for them, maybe they when they collected the data, that's how what they have, right? So it's actually up to you to do the processing, right? So fortunately, in this case, it is not very difficult. But to make your job easy, I will just give you this code so that you can convert it, right? So I'm going to give you this sample code, and then you're going to just change this part here. All right, so this part you have to read in the data table, and then you just convert, right? And then you'll get your BCnosis data set for ready for analysis, right? So this is just to show you what actually happens if you're a consultant and then you get a data set like this, and how you would actually go about processing the data, okay? So this data set actually gives you some exposure about how to do processing, but of course with a bit of hand holding, right? Okay, so and let me go back to the, okay. So this is just partial, right? So the actual data is actually quite, there are many more categories and all that. So it's actually quite long. So I already truncated this table, right? So then the main scientific question here is which, if any, of the explanatory variables are significant predictors of this cyanosis, right? So you can recommend some of this, which one, right? Actually, some of these variables should by themselves give you some clues already. For example, you would expect a workplace that's very dusty to be associated with higher incidence of this cyanosis, and maybe employment length as well. Okay. So those two maybe you already kind of like anticipate, but the rest of them, not sure. All right. So there are several strategies that you can do here. You could try a logistic regression. Because that's something that you maybe have already learned before, right? And it's actually also possible that you can try a very powerful method that's called the regression tree. So there's a very nice software called Guide, which maybe later I will show you around. Okay, you can also use that software to perform a regression tree analysis. In fact, if you use that regression tree analysis approach to approach this problem, for me, I think that will give some kind of recommendation that is actually superior than the use of a regression model, just a logistic regression model. In fact, you can actually do a logistic regression tree, which maybe is something new to you. Okay, so the reason why the standard logistic regression model may not be very may be a bit problematic is because these variables that you consider here, a lot of them, they are actually interacting with each other. Okay, so if you need to include all the higher order interactions, like for example, different combinations of dust and rays and dust and sex and so on and so forth, right? There are all the pairwise interactions. How many pairwise interactions are there? 1, 2, 3, 4, 5. So 5 choose 2. And that would easily give you an additional 5 choose 2, that will be 10, right? That will be additional 10 combinations of explanatory variables, okay? So you have to look at interaction terms as well, okay, before you look at the main effects. So it's actually not so easy to work with a standard logistic model because all this issue about interactions come in. Okay, and then the coefficients, right? So usually the coefficients are not easy to interpret as well, especially if you have done some transformation. But in this case, I think there's no transformation, right? Because they're all categorical. Okay. So and then for categorical variables, if you use logistic regression, what happens is that the if a logistic variable, sorry, if a categorical variable has 3 levels, then it will induce 2 dummy variables, right? One, if you have 3 levels, then you have 2 dummy variables to which are either 0 and 1 to represent the 2 levels, to represent the 3 levels. Okay, so that may actually inflate the number of variables in your data set. Although for this, in this problem, that may not be an issue because I think you have 5,000 plus rows. Later you will see that you get almost 5,000 plus rows. Okay. So so maybe a better solution is to use a regression tree method, right? So this part this question is the hardest one of the 4. So it may take a bit of your time to learn the how to use the software guide to do the analysis. Okay, and once you have the outcome for this analysis from this software, you can make some recommendations to the client about your protective measures, right? Of course, intuitively, this would be something that actually stops them from or reduce the amount of fibers that they inhale in the air, right? So some kind of, but this has to be related to the variables that you actually look at, right? Okay, so I think I've given you an explanation of the data set. So any questions that you want to ask me about these data sets? Any questions? Right, okay, so then if not, maybe you will have some later, right? Okay, so then let me just go to show you how to use permutation test and bootstrapping to that will help you to do questions 2 and 3. All right. So I have the R code in Spectrum, which is this one, example of permutation test and bootstrapping R codes, right? So this one, download this. And then this example uses the urine crystal data set that you actually used in assignment 1. So I use that as an example. Okay. Right. So let's go to the code now. So let me just save this. Okay, so let me see. Let me open the document. Downloads. Okay. Right, so basically, let me see this part here. Analysis. Oh, that's not the correct code. Let me see. Okay, I think I uploaded the wrong. Okay, let me just take a minute to correct that. Okay, so it's been corrected. Let me just download this. Okay, it's this one. So download. Right, let's get back to R. Okay. Okay, so this is the code here. So the first part is basically just reading the data and then extracting the relevant response variable. So this is just to make things simple. So over here, I only concentrated on the urea, right? Although of course, in assignment 1, you work with the entire data set, right? But over here, I just wanted to show the application of permutation test in a simple t-test kind of setting. Okay, so that's why I only extracted one of the variables, okay, just as an example. Now, if you do a standard t-test, basically, you just run this code here. So basically, this is doing the t-test with the relevant information given, right? So the t-test gives you this output, right, where the p-value is 0.02. Okay, and then of course your confidence interval is this -126 and -9, right? And this is your observed statistic. Okay, this is your observed statistic. Basically, you just extract. This is your observed statistic -2.3187. So basically, this is the same thing as the previous one, except that you have a $ statistic to extract the t statistic, right? So you can look at this one, and basically your t observed is basically this value here, all right? Okay. Now after that, these are basically just the ID of the samples where it's no and yes, right, for the crystals. So you just run that. Now over here, this is your permutation test simulator. So basically, you just need to run this. So I'm just going to run this whole thing. Later, I'm just going to refresh you about the theory, right? So this part here will simulate the permutation distribution. You can actually visualize it using a histogram if you want. So you can actually see the distribution of your permutation distribution, right? Which is basically just a distribution of the t statistics that you found from by using the permuted samples as input. Okay, so this is not that important, it's just for checking. So then after that, this part here allows you to calculate the p-value, okay? So this is a two-sided p-value. So sorry, two-sided test. So your p-value has a factor of 2 with it, right? So, okay. Right, so in this case, your p-value is 0.025, right? So basically, the p-value is you have this thing here plus, because this part is basically this is basically just an indicator function, right? Your p-value, it will so if you recall the definition of your p-value, it's the probability of observing a test statistic that is equal to or more extreme than what you have observed, right? So more extreme means to the if your test statistic is already negative, right? Your observed test statistic is a negative value. Then more extreme means to the left side. Okay. If it's if your test statistic is positive, then more extreme means to the right hand side of it, right? So that's why you have to have this thing here. Okay, the plus. Right, later, so this one TOBS less than 0 is either a yes, 0 or 1, right? If this is 1, this will be 0, right? So basically this equation here allows you to just compute the correct p-value depending on whether it's on the left side or the right side, okay? And this one over here is the code to do to use bootstrapping to do confidence interval and also compute the p-value. In fact, bootstrapping permutation test only allows you to compute the p-value, right? So your bootstrapping can do p-value computation and also construction of the 95% confidence interval simultaneously, okay? So generally, in order to do this, so basically, I just run you through the code first. Okay, so here is basically you just take out the subsets with crystals and no crystals, all right? Let's see again. Subset of urea data set crystal. Oh, okay, forgot. So, okay, that's fine. Forgot the hashtag, right? So anyway, that's fine. Then you transform the data for bootstrapping. Now, to use bootstrapping to make inference, you have to work with the, there's some kind of transformation that's needed, right? So the transformation is you take the observation and you subtract the, so this is the observation for the crystal group. You subtract it, subtract the mean of the no crystal from it, and then you add the mean of the entire data set, right? For the mean for both groups, okay? So you subtract the mean of the group, then you add the mean of the entire data set, right? And you do that for the, this is the only transformation that you need, all right? And then after that, let me see. So basically over here, this is, Okay, so basically over here, this is basically just sampling with replacement. All right, so it's basically just executing sampling with replacement. The way we do it is we sample the labels, right? Okay, these are the labels of your no crystal group. So you sample that with replacement. So following the label, we extract the which data that we sample, right? So okay, here's the label, right? And then what happens is you compute the test statistic, right? The test statistic is computed using the transformed data. And the other one is the, you just basically take the difference of the untransformed data, right? The difference between the mean of no crystal and yes crystal, okay? So this part here is useful for making the 95% confidence interval for the sample means. Sorry, 95% confidence interval for the population, difference in population means, right? And whereas the this part here is useful for your computation of the p-value, right? Then you return the pairs of values, right? And then once you have the simulation done for one particular iteration, you can iterate it many times, right? So let's say you do it 10,000 times. So basically you use the S-apply to go about it. And after that, that's it, right? So the first part here is getting the p-value. The second part here is basically you use the percentile method. Basically, you just look at the percentile, the 2.5 percentile and the 97.5 percentile of the bootstrap distribution will give you the approximate 95% confidence interval. So let's try to run this. Okay, run everything, just call source Asian. Just when you type source of this, basically it just runs the whole thing. Okay, so then you could actually look at this one, the quantile, right? And then you can check the bootstrap p-value, which is this one, okay? It'll be slightly different from what you get from the permutation test, but that doesn't matter, okay? Because it's a simulation method, so there will be some discrepancy when every time you make a different simulation, right? But the differences shouldn't be too big. Now you compare that against the result that you get from a t-test, and you can see that the p-value from the t-test is actually quite close to the one that you get from the bootstrapping, almost the same. And then your confidence interval is also about the same, right? From the t-test, minus 126.6, minus 9.48. From the bootstrapping, minus 124.7, minus 11.78, right? So approximately, so both approaches give you the same thing. So as a consultant, you would actually feel very comfortable reporting the result from a t-test and not bother your client with the permutation test result, because both of them are almost the same. Okay, and that actually, so actually in this case, your permutation test and your bootstrapping test results actually give you a lot of confidence to report the t-test results, right? Even though the distributional assumptions of your data are not fulfilled, right? So you're not bothered, because the gold standard here is your permutation test and your bootstrap. right? And since they agree with they support the t-test results, and just make life easy for your client and just report the t-test results, okay? So this is the take-home message from the question 2 and 3, all right? So I'd like you to check whether the result that you get from an application of a standard test is actually the same, almost the same as the one that you get from the permutation or the bootstrap analysis, okay? So, all right, so this one is the example. So maybe I roughly just go through the theory a little bit. Let me see. Share. Okay, so your bootstrap algorithm works like this. Okay, so you have for a let's see, for a set of observations. So maybe you have x1, x2, and until xn, right? Number one, you resample the observations with replacement. Which means so you do something like this. So generating a pseudo sample. So basically, you might actually get something like this. If you resample, so you might actually get something like this. Okay, but the length is still n, yeah. Okay, it's the same length as the length of your original set of observations, right? Okay, then basically it's just resampling. The second part will be after you resample, right? You compute the test statistic of interest. Tx with the pseudo sample, right? So for example, this pseudo sample, you would actually maybe write it as x bracket 1, okay, to denote the set of observations. So this is like a vector, right? Okay, a vector of observations. Okay. So basically, then you will get T of T1 with this set of pseudo sample, right? And then basically that's it. Then you repeat 1 and 2, say 10,000 times to generate the distribution of the test statistics, but with the different pseudo samples, okay? So I is 1, 2, until n. Say no, in this case 10,000, right? And then, so a few things. The SE of the distribution of TI, sorry, the SD, sorry, erase it. The SD of the distribution of your whatever test statistic you're interested in is equal to the standard error of T of X, okay? So this is number one. Then the number two is the following, the 2.5th percentile of 2.5th and 97.5th percentile of your statistic here. Let's see. So let me see. Over here, you can have, for example, this is an example, right? X bar of 1. Okay, maybe I leave that out for a 2. So, okay, maybe the next one. Just keep it simple first, right? So let's see, this one is this is for a one sample case. Right? Okay, so this is a one sample case. The one that we look at is in questions 2 and 3 are actually the 2 sample cases. So let me just clear this. So then you have your bootstrap algorithm. So this is for the two sample case. Right. So again, first part is you have observations. X11, X12, until X1, maybe N. This one is from group 1, right? And then you have X21, X22, until X2M, right? So this is group 2. So then you resample, right? You resample from group 1. So you get maybe some pseudo sample like this, X14, X11, X11, X17, and so on, right? To X16, for example. So the length here is N, okay? And you also resample from group 2. These are all with replacement, okay? So this will be X25 maybe, X23, X22, X24, right? So there are M of them, okay? So so you created, these are pseudo samples. Right, okay, so And after that, you could compute the test statistic of interest. Tx using the pseudo samples here, right? Put x 1 1, x 2 1, right? So this is a vector, right? This one I just denote it by I, okay? Right, you can compute the test statistic of interest using this. And also, maybe something like if you are interested in the confidence interval, suitable statistics for the confidence interval. For example, you could take the sample mean, right, of 1 using pseudo sample 1 minus the sample mean for group 2 using, okay, so it's I. Okay, so because this thing here, right, they estimate your mu1 minus mu2. Okay, so this will be this part here will be useful for confidence interval, right? And this part here will be useful for the p-value. Okay, but before that, let me see. Once you have done okay, maybe the transformation. So then over here you have a transformation. X 1 1k, subtract the mean of 1, then you plus the mean from both groups. Okay, so this is a transformation denoted by x 1k star. Okay, so this x2k minus x bar 2 dot plus x. So this is a transformation that you saw just now in the code, right? So you keep both of them. So this one you could actually do 2 sets, right? So resample, you get this. So you resample using the same index, right? Same indices, okay? So you have one pseudo sample that's like this, and then correspondingly you have a pseudo sample that's like this, okay? The index is the same, right? But the values are, one is the transformed, the other is untransformed, okay? Okay, so this one is x 5, x 3, x 2, so x 4. Okay, so this one you actually have to use the one with the transform, and this one is without the transformation, right? Okay, this one no transform. Okay, so then after that, after these 2 main steps are done, then number 4 is basically you repeat 2 and 3. Let's say 10,000 times to generate a distribution of Tx, and also this, the distribution of this, okay? All right, and finally, number 5, you compute p-value using distribution of dx, and the percentile, the 2.5 percentile and the 97.5 percentile, they form the, so they are the lower and upper limits of the 95% confidence interval for mu1 minus mu2, okay? Right, so this is an example of using the bootstrap algorithm to do inference, okay? So so this is the general idea. So you, it's actually simple enough to run, okay? Although bootstrapping can be, you can always design bootstrapping for complicated designs, right? But this design is the simplest one, right? The 2-sample case, all right? So the code has been shared with you, so you can make suitable modifications of it for the data set in question 2 and 3, all right? So that you can actually get your results, okay? For 3 is ANOVA, so instead of the t-test, you have to extract the F statistic out from the ANOVA result. So let's go back to that. See, ANOVA will be so if you want to do ANOVA, you have to use the function AOV, right? So you can put a question mark on AOV, right? And share. Okay, so you can read the documentation in AOV. Look at the example, how it is done, right? So that will allow you to run the analysis of variance by calling the AOV function, and then you can extract the necessary statistic, right? Okay, so a little bit of coding for you. But generally, the bootstrapping code has been shared with the permutation test code has been shared with you, so you just need to modify a little bit, right? You can discuss this among yourselves, right? In fact, if you can form some discussion groups among yourself. Some of you might actually be better at the coding, and then you can try to help each other out with the code, right? And then of course you may have different perspectives on the interpretation, so that will be good as well, right? If you can have some discussion among yourself, okay? Okay, let me see. The data set is actually, let's go back to the data set. Okay, so the time that so the data sets are here, right? We can look at that. Okay, so the data sets are there. So one is 2 of them are in the text file. The one is in CSV. So to read the text file, you use the read dot table function, right? CSV read dot CSV. Okay. And I give you 2 weeks to do this. So the submission time is 4th of June, right? 6:25. Okay. So you can start working on the simpler problems first, and then I think I might actually spend a bit of time to make short video recording on how to use the guide program. Okay, that one maybe next week I will talk about the program. So I'll try to get the radio done before that, so you can read the video about how to run guide and get results. Okay, so I think there should be enough time for you to do it. So ideally, you should finish the first 3 questions in this week, and then you spend the next week working on question 4. Okay. All right. Okay. So we are about to end at 9:30. So are there any questions from you? Do you have any additional queries about the assignment? Okay, so do you need to submit the assignment in Microsoft Word or PDF? You please convert it to PDF. All right. Of course, you can do it in Word, but yeah, it will make my marking easier if you convert it to PDF, right? Because I need to convert it to PDF anyway. Otherwise, yeah. So please do convert it to a PDF. In this case, the R codes that you have used, right? Please put them in an appendix, okay? So you solve the problems 1, 2, 3, 4, right? So then you don't put the code. You please don't put the code inside every question, right? Just give the solution that you obtain from running whatever code that you have. But you keep the code like after you have done everything, right? You put a section called appendix, and then you put the code that you used for each of the sections. Okay, so that will be cleaner and easier for me to check, right? And please put just the code, right? I don't need to see the execution. Okay, putting the code means you just give me something like this, right? And not things like, you run this and then you have all the prompts come out. Please don't give me that, right? Because that is just showing what you got on the screen, right? Just give me the code and in the appendix, that will be enough. Okay. Do you have page limit? There's no page limit because this is an analysis, right? It's not a consultation report, so I didn't mention that. Okay. But of course, yeah. Okay. So the amount of work that you need to do, you can more or less gauge it from the amount of marks that's allocated, right? If you have any questions that you want to ask, you can do so anytime, as and when you work on them, right? You can just send me some flock messages and I'll reply them. Okay, so any other questions from everyone? Amy, you have any questions? Right. Okay. So I think if that's the case, okay. So we come to the end. So happy holidays, everyone, and yeah. So I'll see you next week on Thursday again. Okay. So okay. So that's all for today. Thank you for listening.